Shall we start? Hi, everybody. One quick note. One thing. I mean, many of you have, I think, must be all the groups defined. I mean, if your group has not been defined by tomorrow or so, just let me know. Okay, you can write on Piazza. Definitely, the TAs would take care of it. So, but your group has been defined, so you can upload your proposal, and you don't need to worry about the proposal. I mean, of course, if there is any issue, I mean, 99% it wouldn't be any issue. But if there is anything like people think it might be a bit like risky to do that, they're gonna let you know. Okay. So regarding the projects and one thing else, I mean, you asked me for sample questions, and I just put you sample practice on Kirkus, right? So you have written question part where you have some sample questions. You can just get the feeling how the exam would be, and then there is a programming part, which is about the data pre-processing we have in this chapter. I'm not going to cover it in the assignments because it's not that, I mean, it's not really deep learning, but I just wanted to give you a kind of practice if you wish to have some sample practice and using Pandas library to do data cleaning. So that's it, and then let's get back to the lecture. So the other session we ended up here at the beginning of RProp, resilience backpropagation, and there is maybe we just recap what we are doing. So we basically ended up the last lecture, last chapter by this message that, or this conclusion that if we want to just train a model, we basically need to use a stochastic gradient descent with some size of mini batch, right? And then we said that if we just go and do the implementation of the stochastic gradient descent with the most naive approach, then it's going to be a bit of trouble because this is not numerically that stable. And there are a bunch of algorithms developed in the literature which we nowadays mostly use them. And those optimizers, I mean, you have a very long list of them, but we just wanted to just mention a few of them which are the most dominant one, or the key ones which use the, the most important ideas in improving the quality of the optimization process. So I told you that there are two main processes. So the first one was the idea of learning rate scheduling, meaning that you just try to somehow play around with your learning rate in every single iteration, such that gradually, I mean, as you go through your training process, you're going to get close to the local optimum faster. And just to remember, the whole purpose is to improve the speed of our convergence. And what is the ideal speed for convergence? What is the best thing we could think of, like in practice? We call it linear convergence. And how does it change with the error that we want to get close to? Logarithmically, right? So if you wanted to have, like, if you want to be 10 to the power minus 3 close to the optimal point, then the number of iterations you need to do with very good algorithm which linearly converges to the solution, it's going to be of the order of the exponent. So some constant times the exponent, which is 3. 10 to the power minus 3, so 1 over 10 to the power minus 3, I mean that. But if you have sublinear convergence, which is usually the case in practice, then it's going to just converge slower, right? And this could be as bad as the one we have seen, which was reversely proportional to that epsilon value. So it means that we could have like 1,000 times some constant number of iteration, which is a huge difference. So the whole purpose is to just improve that speed, right? And then we just wanted to find out a few ideas. The key two ideas, one of them is to play around with the scheduling rate, learning rate, schedule it. And the second one was the idea of momentum, right? And the momentum idea was simply that you get your gradient, but you do not simply pass it to your gradient descent algorithm, but you compute the moving average of this guy with what you already have computed. Yeah? And then you get this moving average going on in your algorithm. We said that this beta is usually something close to 1. So 0.9 is a kind of classic choice. And these two ideas, if you just combine them, like moving average and the idea of scheduling the learning rate, these two gonna pretty much describe most practical algorithm we use or optimizer we use in practice. So one idea, which is a kind of a step forward in optimization or training of neural networks, is this idea of resilient backpropagation. People usually call it RProp. So it's not really about backpropagation, it's just optimization. So it really refers to the gradient descent, not backpropagation. All of them use the same backpropagation. But I mean, people used to just refer to these two things like exchangingly, and then it somehow got this term. So it's a paper written in 1992, which you can click on this blue text here to get to the paper, to see the original paper. So what is the idea here? The idea is basically what you had seen in first assignment you had. So if you remember in the first assignment, you wanted to just solve that simple dummy example of projectile, and then you had two parameters, right? W1, W2. And then when you looked at those parameters, you had two options. You could just choose one learning rate, which you always multiply with the gradient, the whole vector, or you could think of individual learning rate for every single weight, right? So you could have two learning rates, and each of them was allocated to one of the weights in your model, and then you just train or somehow play around with those two things. And what you had seen in that assignment was that if you have two learning rates, then you potentially can find a choice that somehow makes you converge to the optimal solution within just one iteration. Whereas it was not necessarily the case when you had a single learning rate, right? So moral of the story, if you have a multidimensional thing, if you could just train, we talked about this in the first chapter, if you could just train every single weight with its corresponding learning rate, then you're gonna do much better. But the problem gonna get very complicated. And then they came up with some idea that they could do it remotely, so they don't need to just tune every single learning rate individually. So what is the idea? Let's just start with a very simple case where I want to just optimize a one-dimensional function. So my R function, I mean, we usually are optimizing the risk. So my risk function, R hat, is now a function of just a variable, right? So this W is just a scalar. So if this is the case, then, I mean, what do we do in the standard gradient descent? We just compute the gradient at one particular weight, and then we just compute the next weight to be the previous weight minus learning rate times the gradient, right? Which is here the derivative. Now, the thing that we are going to do here in RProp is that first of all, instead of the gradient, we only look into its sign. Meaning that its amplitude, we just shift it to the learning rate. Okay? Because if I just multiply this eta with the amplitude, the magnitude of this gradient or this derivative, nothing going to change, right? So I'm going to just use the sign. So I'm going to replace that g by the sign, and then I'm going to shift the amplitude or put the impact of amplitude directly inside this learning rate. Okay? So it's a kind of scheduling, right? Now, how do I do this scheduling? This is where the RProp shows up. Okay, so the RProp has its own way of scheduling, which is a kind of automated way. And we're going to talk about it. So basically what you're going to do, you're going to take a couple of parameters. So there is a kind of hyperparameters mu plus, which is a number more than 1. There is a mu minus, which is a number less than 1. And then both of them, of course, positive. And then you have some maximum limit, minimum limit. And then there's one scheduler here, which is going to get your current learning rate, your current gradient, your previous gradient. And out of these three, it's going to compute the new learning rate and put it here. Okay? So the R-prop algorithm here up to this point is basically the gradient descent that you know. The only thing is that now you're not using the magnitude of your gradient anymore. You're only using its sign, and then you schedule the learning rate. Clear? Now, the only black box here, or blue box actually here, is this R-prop scheduler, right? Which we want to find out. So how does it work? So this is how the R-prop scheduler works. Now, what it's going to do, first of all, let's assume that I have this mu plus, which is larger than 1. Now, when I look at two different gradients, like gradients of this iteration and the previous iteration, and I'm looking only into its sign, the sign could be either the same or different, right? Now, let's consider the first case. So the first case is when the gradient sign of gt, is exactly the sign of what I had in the previous iteration. Okay? Now, if the sign of my gradient, I mean, right now think about a function, as I said, just scalar function. If the sign of my gradient, which is now a derivative, if the sign of this guy and this guy are the same, here it is negative, here it is again negative, what does it tell me? It tells me that I am still going towards the minimizer, right? So I should keep on going. So since this is the case, since the sign is not changing, so I do understand that the way that I'm going toward is the right way. So what I'm going to do, I'm going to just increase my learning rate, because I'm going to say this is the correct way to go, just go faster, right? So I'm going to multiply my previous learning rate with something more than 1. Clear? So I'm increasing the speed, yeah? So I'm going faster. And of course, I can always put some eta max, so there is one maximum value for my learning rate, which I do not exceed that, okay? So I just keep increasing my learning rate up to some point, and whenever I reach that maximum point, I just keep that one, okay? So this is the first case where the sign is not changing. But what's going to happen if the sign changes? Like, again, look at this function. What's going to happen? I mean, here the sign is negative, right? Or maybe here. Here the sign is negative, correct? Where do I have the sign positive? Where do the signs start to change? When I pass that minimizer, right? At this minimum point, I have 0 derivative. And after that, the sign starts to be positive, right? Now, if I jump from here to here, then what should I do? I should get back, of course. That is the one which the sign tells me. But should I go faster back or slower back? I should go slower, right? Because I do know that I have passed the minimizer. So if I go faster back, I'm just going back to, I mean, even before where I was, right? But I do know that the minimizer is not there. So I should take a smaller step, correct? Everybody's clear? So if the sign is not the same, so I'm going to choose one value mu minus, which is now smaller than 1. And then when the sign is not the same, then I am going to just reduce the amplitude of my learning rate with this factor, which is smaller than 1. Clear? So my learning rate was something. Then I'm going to say, OK, I passed the minimizer, so I'm going to, for example, move back with half a step. So I'm going to get to this point, right? I took this step eta t minus 1. Then I passed, so the sign got changed. Now I'm going to have, say, for example, mu minus is exactly 1/2. So my eta t is going to be eta t minus 1 divided by 2, right? So I'm going to just get back with a smaller step so that I can get to the minimum, right? Everybody's clear? And of course, again, you're going to have one minimum value, which is going to just bound your learning rate, right? I mean, you reduce your learning rate up to a point, and when you get to that minimum, you don't reduce it anymore. Clear? So you got the idea of RPROG? So very easy, right? So you're going to keep going whenever, I mean, you can always think of it like that. So you're just going down. So you see that you're on the right track, so you make it faster, faster, faster. But the moment that you pass that minimizer, you're going to get back, but this time slower, right? You keep on doing this. Now, you can just have a simple visualization of this, like, for example, at this point, this very start point, say my learning rate is proportional to this guy. So this is the size of my learning rate now. And now, what is the sign of the next point, or the gradient at the next point? Is it the same or is it different? It's the same, right? Both of them have negative sign, right? So what I'm going to do, I'm going to increase my learning rate. Yeah, I'm going to take larger steps. So I'm going to have the larger step. Again, I'm going to see the same sign, so I'm going to do again larger. But when I do it larger, then I'm going to pass the minimizer, right? And then at that point, I'm going to say, okay, I should get back, but I shouldn't get back as, you know, as large a step as before. I should take smaller step, right? So I'm going to take smaller step, right? And if I do that, then I have more chances to get close to the minimum as compared to the using previous learning rate. So that is the idea of RPROB. And you might have this question that how can I just extend it to the multidimensional case? Quite easy. You just look at every single entry inside your gradient as a single guy, and then you apply the RPROB on that. Yes?
Yeah. We have some local minimums and global minimums and minimums. Am I right?
Right.
And if we do that, we always start in a local minimum. Okay, but
Yeah, sure, but
learning by increase and something like that, we make.
Yeah, but that is, I mean, that you should come to kind of peace with this fact that you are never going to get into a global minimum. But what you're saying is always something like this, for example, you have. And then it might be a bit like, here is the global minimum. And if you're working somewhere here, the chance that you get into this one is pretty much zero. Yeah? But you might say that, okay, if I am here, I would be happy if, first of all, I get here. Secondly, I get here. I would be the least happy if I get here. Yeah? Whether in the training we're getting really here, here, or here, I don't know. Yeah? This is the only way that you can examine it is based on intuition. And this is something you're going to do before you let your algorithm to run, right? So for example, you start doing the training, and say this guy here that I'm showing you, this is the cross entropy. And as I told you before, this cross entropy, when you are really training it properly, then this should get somewhere close to zero, right? So maybe this point, which touches exactly this minimum, this is zero, right? So you do know that this guy should be zero. If here it is, I don't know, 0.7, what is obvious to you is that this is definitely not a very good local minimum. But if you get into some value like this, which is, I don't know, 0.09, then you would say, okay, this is a much better one. Yeah? So this is something that you're going to try by validation. So you're going to let your algorithm run for a couple of times. You do some random jumps, things like that. And then at the end of the day, you're going to say that, okay, this is a kind of very bad trap point. So I'm going to jump or start with those choices which takes us here. But the point here is that this is a kind of dumb example when we have a very low dimensional function. In practice, you have a huge dimensional function, which you pretty much never can do this. The only thing that you would be happy is that you just get next to the to get into the very next minimizer. Okay, so this is not the issue here right now. The issue that we have is that we do know that, for example, we start here, and definitely we're going to get here, but we just want to get here as fast as possible. Yeah? And then the question is how we can do it. I mean, we can do like learning rate scheduling, we can use momentum, things like that. Because when you are doing SGD, you are not always finding the right gradient, right? So sometimes you're going to give you negative because you are doing it randomly over a mini batch. And then you just want to reduce the chance of that happening. Yeah?
for example, we see a loss of 0.09, that it is still very high to us, and we know there is some better minimum that we have.
This is something coming out of feeling you're going to have to the problem. If the problem is very easy, then you can try it multiple times, like is classification of MNIST. I have done it thousands of times, so I do know what is the right value. But if it's a totally new problem, who can say, all right?
Okay, so there is no, let's say,
No concrete way of checking that. It just comes out of practice that you can get. And at the end of the day, you can just talk with like metrics which are like sensible to you. Like you evaluate the accuracy of the trained model. Yeah? And if it is like very accurate, then you don't care anymore about the loss minimizer.
So in practice, we still depend on the accuracy to decide whether we have trained to a good minimum.
Exactly. So, I mean, we do all of it in order to get that thing right? But at the end of the day, we can just test it because that is the only thing that we have a kind of a sense about, right?
So if the input dimension is high, then after we have trained a model and we see a low accuracy, there is a chance that we are hitting a bad local minimum and we track there.
There is a chance, but this is not the only chance. This is not the only reason. There are a bunch of other reasons as well, but it could very well be, yeah? But then it depends on the model that you have defined. It's not only about the algorithm that does the minimization for you. It's the fact that how you have defined your architecture, because if you make your architecture to be like it has billions of weights, but it's very sensitive to only one weight or only a few ones, then that is not a kind of very robust or stable model. And then it could potentially make you like, I mean, you just try it 2 times, once it works, once it doesn't, right? So those things are the things which we can engineer and we can control. Those are things that we're going to focus on, as you're going to see through the lecture. But the fact that whether we're stuck here or here, I mean, it's always a kind of theoretical question, and you can always keep it in mind as a kind of possibility. At the end of the day, when nothing works, it might be the case. But this is not something that you can like feasibly resolve very, very accurately. Yeah. Yeah. So, yeah.
Is the intuition of our probe that we are converging exponentially, like the distance is going exponentially slower, less, I guess?
Yeah, exactly. I mean, you are training that guy somehow exponentially, but you're going to see that this mainly comes from the fact that you're going to apply our probe in practice for multidimensional case, which we have individually on every single dimension. Okay, this is what I'm going to tell you next. So this is the key point that our probe is going to help us. Okay. Any questions? Cool. Yeah. You got a question? No. Okay. So now, what's going to happen if we have a multidimensional case? Meaning that this weight is not anymore a single parameter, it's a vector of weights, which is the thing in practice, right? So you can basically apply our probe same as before. So you're going to compute the gradient, which is now a vector, and then you're going to have same thing like a mu plus, mu minus, eta max, eta minimum, eta mean, and then for every single entry inside this gradient, the thing that you are going to do is going to just update your corresponding eta. Okay, so you first start for same learning grade for everybody, but each time that you want to update, you are going to look at the sign of the gradient entry. You give it to that rprop scheduler, and this guy is going to just find you the next value, yeah? The next learning grade. Okay, so I guess this is now obvious for you that when you start, I mean, every single weight in your model start with the same learning grade, but as you pass through the training process, those learning grades are going to change, right? So if you have 2 different weights, initially, so say I have W1 and W2, then the thing is that I'm going to have a gradient which is G1 and G2, right? a gradient of dimension 2, right? And then initially I'm going to say that this guy has learning grade eta. This guy has also learning grade eta. But if the sign of this guy changes, this one doesn't, then this one and this one are going to change or get updated differently, right? So through time, as time passes, as the iteration in your training algorithm pass, these guys are going to be two different things. You agree? And this is the key point. I mean, you are not doing anything here, complex. You basically apply rprop on every single entry, but that guy is doing like entry-wise update of learning grade for you. And this is the key factor in the whole rprop. Okay? So you are basically going to just apply one-dimensional rprop for every single entry of this weight vector now, and then you just keep on doing the training. Yeah?
Sorry, what does it look like? One-dimensional?
Exactly like what we did in the previous slide. So as I told you, like you have a weight vector of dimension 2. Say, for example, this is t equal by 1. You got the gradients, and this guy is 1, 1. Okay? This is your gradient, which is a vector now. This is your gradient at time 1. And then at time t equal by 2, your gradient 2 is now, for example, 2 minus 1. Now, if you start with the same learning grade, at this point, you are going, for example, say mu plus is 2, mu minus is half, and then your eta, 0, the initial learning grade, this eta is, for example, 1. Okay? So here you have the same sign still. For example, you're going to make it double, right? So after finishing with this guy, then you're going to say, okay, both of them are going to get multiplied by 2, right? So meaning that this, now the learning grade here, so eta of the first entry at time 1 is going to be 2. Eta of the second guy, eta 2, at iteration 1 is going to also be 2, right? But after the second iteration, you here see that the sign has not changed, so you keep on increasing this guy. So eta of the first entry at iteration 2 is going to be 2 times this one, which is now 4. But for this guy, since the sign has changed, then you're going to get 2 divided by, or times half, which is going to be eta 2 is going to be 1. And then as they pass through time, they are going to get totally different things, right? So you keep on doing it. Every time that you want to update, you simply get this guy, multiply it with the gradient, and then subtract it from your current weight. Clear? Yeah.
One more question. The optimizer that we have covered so far and what we are going to cover, including atom, are those optimizers all linearly converge linearly?
I mean, depends on your batch size, things like that. Like if you are just, they are converging much better than naive stochastic gradient descent. But I mean, depends on many things. So I cannot say really linearly. If your problem, it depends on your objective function as well. You know, if you want to prove it concretely, then you do need to know whether your convergence function has your objective function has a kind of nice properties. Because if you remember, I told you that this linear convergence is not only the thing of the algorithm, it also depends on what you're optimizing. If that is strongly convex, then it's going to converge, of course, linearly. But when it is not, then it's definitely sublinear. But that sublinear is better than naive stochastic gradient descent.
So that no optimizer guaranteed to have linear.
It's a kind of strong constraint. It's a kind of strong requirement. So you really need your function to be like, if you have a linear regression problem with nice, strongly convex objective function, loss function, then of course that could. But in practice, no, you cannot get that.
And is there any reason that everybody prefers atom than other?
Yeah, sure, because that is working much better. That is more robust as compared to those ones. and you get potentially a boost in the conversion speed. But this doesn't necessarily mean that you are getting linear, yeah? But you are getting much better than the other. Not much better, but better than the other ones.
Okay.
No. Of course. So, now, everybody's clear about how we can apply rprop on the multidimensional case? So, now, one thing about the rprop, first of all, is that, I mean, as I told you, you're going to usually start with one specific learning rate for everybody, but then gradually you're going to update with a couple of parameters, like these are classical choices, and then this is going to just make your learning rates to be different through time. Yeah? This is the first thing. The other thing is that those maximum and minimum values are not that crucial, because gradually at some point when you get close to the minimizer, you're going to jump, I mean, just increase, decrease, increase, decrease, and they are not going to show up that much. Okay? But you can, I mean, I think most packages have their own default values. You can just rely on that. And one thing else that is interesting is that, or interesting to know, is that it's better that you do not do such a choice, right? So your plus is 1 over your mu minus, because then it means that when you pass the minimum, then you're going to get exactly the same step size. You don't want to get back exactly where you were, right? So this is not a kind of cool choice. And yeah, that's it. You can easily just access it over Torch. I mean, you just check the Optim library and then the module, and then you have it already implemented with all those parameters defined. And this was a kind of, as I told you, a step forward in the optimizer design, but it has one particular issue. And the key issue with basic form of rprop is that it can only work fine when you have a full batch training, meaning that you're really computing your gradient over a large number of samples. You might wonder why this is happening like this. So I have tried one dummy example for you to explain you why this is happening, or why this is working very well with full batch training. So let's just consider this dummy example. The dummy example says that, say you have a one-dimensional case, so we don't have any vector like that one here, or weight is just a single scalar. And then we are doing, we have a full batch of data, but we are not doing full batch training. We're just breaking it into 4 different mini batches. And then what we are going to do, we are going to compute the gradient over the first mini batch, and then we just apply 1 step of gradient descent, right? And then the second mini batch, the second iteration, and so on, right? Correct? Now, say that your gradient or your derivative, when you compute it over the first mini batch, is 0.1, the second one is 0.1, the third one is 0.1, but the last one is 0.5, okay? Now, I do know that those gradients are computed at different iterations, but say that those iterations are pretty much close to each other, okay? Now, what does it tell you? What if I would have computed the gradient, or this derivative, over the whole full batch? What would have been the gradient when I computed over the full batch?
Summation or average?
Average of these guys, right? Because this is computed over 1/4 of your data. This is computed over the second fourth, and so on till the last one. So the average of these guys, and of course they are going to change a bit because you are changing iteration, but what you can say that since this guy is 0.1 and this guy is minus 0.5, I cannot be really sure that this 0.5 really means that I should move in the positive direction, right? But what if you use rprop here? Rprop is going to look at your first gradient, and it's going to tell you, okay, this is positive, right? So since it is positive, and say that the previous one was positive, so it's going to just use this sign +1, and then it says, okay, whatever the learning rate was, I'm going to increase it, right? Then it goes for the second one and says, okay, this is still positive, so I'm going to again increase, and then it goes for the third one, again it increases, and it only starts to decrease it when it gets to the last mini batch, right? So this is going to be some sort of issue when you are doing mini batch or you're relying on your mini batch estimation, especially if the variance of your mini batch estimator is quite high. It's not very, very small. So meaning that in a basic form, if you would have had the full batch risk, then you would have updated this guy pretty much by gradient close to 0. But now what you're doing, you're just taking 3 steps by rprop forward. In each step, you're just increasing your step size, and then you just start to get back at the last iteration, right? And then, of course, this is a dummy example in 1 dimension, but if it is really in very high dimensional scenario, it could very well be that you are just going to lose or get past the minimizer, and then you potentially could have issue. I mean, you take much more time to get back to that minimizer. Clear? So did you get the idea? So moral of the story, since you're just using the sign, and then based on that sign you are just deciding how to move, this could potentially give you higher order of sensitivity to the error that you have in your stochastic gradient calculation. Great? Sorry. Correct? Great. Correct? Huh? You got the idea? Good. So if you got the idea, so this is the main issue, and this is something that you can check it numerically. So the idea to resolve it is what we call it RMS prop, and that was originally proposed by Geoffrey Hinton. You know him, right? You know that he got the Nobel Prize today, right? Okay. So I mean, it's a coincidence that we have his name on the lecture today. So when he got the Nobel Prize, but yeah, the key interesting thing about this one is that actually he never published it. It was in his lecture notes. So he came up with this fact that R prop has this issue, and when he was teaching, he just came up with some new idea that he put in his lecture notes. So what is the idea? What he says that okay. The key factor here is that we're not using the amplitude of the gradient, right? So we need to somehow use it, correct? So how we can do it, he starts to look at the rprop quite differently. So this is what you are doing in rprop, right? So you're going to get your weight in this iteration. Then you have your learning rate, which through time has changed for every single entry, right? So it's a kind of vector of learning rates, and then you multiply every single guy to corresponding gradient, right? So it's an entry-wise product to the sign of gradients, correct? This is the way that we do the update if we just want to write down the multidimensional in one formula. Everybody's clear? Now, what we can say if it's obvious thing, but if I have x equals by minus 5, then what is the sign of x? It's minus 1. Can I write it down minus 5 divided by 5? Sure? So now if I write sign of x is x divided by absolute value of x, you agree? Correct. Okay, great. So you got the idea. So he's going to write this sign to be the gradient divided by its absolute value. It's the same thing. You didn't change anything, right? Now, you're not using, you are somehow using the amplitude of your gradient, but you're using just the amplitude of the gradient in that iteration, right? And we do know that that amplitude of gradient could be very noisy because our estimator is computed over a small mini-batch. So what we can do to reduce that noise? Any idea we had up to this point that helps us reducing noise? Moving average, exactly. So you can just go ahead and compute this, or replace this guy with the moving average of the amplitudes. Okay? But in this algorithm, we don't exactly use the moving average of the amplitude. We use the square root of moving average of the squares. This is why we call it root mean square. Okay? So let's just break it down. So we are going to just replace this guy with its moving average. But what we're going to say that the absolute value of x is basically the square root of absolute value of x squared. So what we are going to do, we compute the moving average of this guy, the square root of x, x squared, and then each time that we want to do the normalization, we just replace the square root of it, okay? So what we are going to do, we are going to just start with some, say, v equal by 0. So for every single entry inside our gradient, we start with 0. Then in the first iteration, we are going to take the gradient squared, right? And then second iteration, we're going to get whatever we had from before, compute the moving average of that one. So this is vt minus 1 with the new gradient squared again, right? So what we are doing, we are just computing the moving average of gradient squared, right? And then instead of putting that, instead of this absolute value here, we just put the square root of this v here, okay? Everybody's clear? So you're going to just normalize instead of gt with the square root of v. And this is going to be RMS prompt. So you start, say, with 0 v, and then you're going to compute the moving average in each iteration. And each time you want to move forward, now you're going to just replace this moving average, square root of it, and then you would say this is a better estimator of that absolute value of g instead of having the absolute value of g in that particular iteration. This is potentially less noisy. And because of that, it's going to give us much more reliable estimate. You get the idea? Yeah.
And are we changing the learning rate of like our prop?
Yes, we do the same thing. We do the same. I mean, basically, sorry. You are not changing it anymore because you start with eta, yeah, and then you potentially do that. But that 1 over a square root of v is now the kind of scheduler that is getting multiplied to your learning rate, right?
So that we can apply two at the same time without affecting each other.
Yeah, of course. Yeah. So you are potentially, I mean, you can think of this a square root of vt, this guy. This is a vector, right? This guy is a vector, correct? Because v is a vector. You're doing it for every single entry. Like you had 2 entries, say this was 0.1, 0.1, and then you changed it, it's going to get, I don't know, 0.1, 0.2. What you're going to do in the second iteration, you're going to get this one squared, which you had from before, then multiply it to some beta, then this guy is squared, multiply it to 1 minus that beta, and then you add them up, right? So as you pass through time, this vt is one vector, and this vector has different values, correct? And then you compute square root of 1 over square root of it, which is again a vector of the same dimension. So you potentially still have a sort of entry-wise learning rates that you are not designing by hand, but this is getting trained by this moving average, or getting scheduled actually by this moving average. But you do know from our prop that this is somehow proportional to the right direction or the step size that you need to go in that direction, that particular direction. Everybody's clear? Yeah.
So could you repeat the part why we use the square root of v, like instead of the absolute value of the?
I mean, the main reason is because it depends on the statistical model you consider, but you can show that this is going to be a better estimator. Yeah, of course, but if you replace that one also by absolute value, the question that your friend says is that why, instead of a square root of v, why we don't just compute the moving average of the absolute value of g? Again, with beta equal by 0, it's going to be the same thing, and you can do it potentially, but this is, numerically you can see that this is more stable. This is going to help you more, but if you want to know what is the reason behind it, this is going to be a better estimator for what you are looking for as compared to that one. But it needs a bit of more, derivation to see that clearly. Yeah? Yep.
So that if my math intuition is correct, we are just favoring the current gradient because we're squaring that, but not the previous v. And then we can
No, we are actually choosing beta to be very close to 1, which we are favoring the already available estimate, because that has been averaged over a long window, right?
That brings another question. Why don't we just change the value of beta instead of just squaring the current gradient? Because I'm thinking if we're squaring the current gradient, then we apply a square root, then we are favoring the gradient of the g, the right gradient there.
But that is not the right gradient.
Mm-hmm.
That is your estimate, right?
Mm-hmm.
You computed it over 1 mini batch, correct?
Mm-hmm.
And this is a noisy estimator. So you're favoring that one less because you do know that it is much noisier than this one. This is average over a long sequence. So it's going to have less variance, right?
Mm-hmm. But then if you are not favoring the current gradient, then why do we apply the square root? Then we apply the square then square root. Why don't we just use the magnitude if we are not favoring that?
No, because you need to, if you want to still have the square root here, you definitely need to have a square here.
Yeah.
Because that guy, when it comes into your moving average, it's going to remain there forever, right? I mean, your VT is going to include your GT. VT plus 1 also has GT. VT plus 2 also has that one. So it's going to remain there forever. So if you want to have the same order, then it's going to be squared definitely. That's going to make order problem, like the order of magnitude that you are adding or multiplying things with. So that one should be here, but I mean, you might think that it is for one single entry, it's not going to impact that much, but when it passes through time, it's going to impact, really. Yeah. Any questions? So you got the idea of RMS prop? Okay, great. So then what you can say here, I mean, if you look at this guy, again, what you can say RMS prop is basically, again, using a kind of RProp-inspired learning rate scheduling, because RProp, the only thing that it does is to schedule properly the learning rate without you needing to come up with any idea for that. It does it for itself. Now, RMS prop does it the same way, right? So you are using still stochastic gradient descent, because as I told you, you can take this square root of VT times eta, all of it together, as kind of one vector of learning rates. And then you are simply multiplying it with your gradient at that particular time instant. And then you're just moving with that one, right? So it's still stochastic gradient descent, the same thing as before, only you have your learning rate being scheduled by a kind of RProp-inspired idea, okay? So maybe you keep it this way in mind, that when you talk about RMS prop, you basically take the idea of RProp for scheduling your learning rate, but still you're doing a stochastic gradient descent, meaning that in every single iteration, you're using the sample gradient that you compute. Clear? Okay, so there are a few things I just wanted to mention here. So one thing is that, of course, I mean, your beta is usually get close to 1. I mean, you usually take it even more than the beta that you use in momentum. So, I mean, choosing, I think, 0.99 is totally fine, okay? This is going to be kind of typical choice. So you need to really put it close to 1 because you want to rely on your a better estimate, and then again you can just simply access it in your optim. Okay. Now, do you have any question? Everybody's clear? Okay, so let's just finish with the last one, which is the ADAM. And ADAM basically comes at as the abbreviation for adaptive ada momentum. And then, I mean, of course, you see that there had been some sort of intention, so they wanted it to be ADAM. So yeah, this is a kind of idea. And basically what you do in ADAM, here I told you RMS prop is stochastic gradient descent. The only difference is that you are scheduling by some sort of idea which you got inspired by RProp. right? Now, if you replace that gradient with a momentum, then you're going to end up with atom. So what do we do in atom? We basically combine the two ideas. So we get RMS prop, but in RMS prop, after we just update that 1 over square root of Vt, then we multiply it with the gradient, right? So if you get back here, you multiply at the end with this red gradient Gt, right? If you replace that one with the moving average of Gt, then it's going to be atom. Clear? So what you do here, you basically just use momentum to update your gradient, and also you use RPROB inspired sort of normalization to schedule your learning rate. So if I want to just write it down here, so you're going to start with some sort of initial momentum for your gradient, some initial moving average for your variance, or this v vector vt, which is the gradient squared, and then the thing that you are going to do is that you're going to update your momentum, which is going to be simply a sort of moving average on your gradient, and your v vector is going to be a moving average on your gradient squared. And then each time that you want to just do one iteration, you basically just get your previous weight, you just multiply it with eta over square root of vt times the momentum, okay? So you're using the better estimate both for gradient and for variance. And this is going to be atom algorithm. Clear? So nothing weird. You basically do the same idea as in the stochastic gradient descent, only you are replacing everything with better estimates. Everybody's clear? Great. So one thing that you should just pay attention to is that all of these pseudocodes that I have shown you here, they are, of course, very simplified version. When you want to implement it in practice, I mean, I do know that you most probably use available packages, but if one time you want to implement it, there are some numerical tricks. Like, for example, you initially start with some, larger choices of beta, and then you just reduce it after a couple of things. You never start with absolutely zero. You add some sort of constant to just make everything numerically stable. I'm not discussing those things here because they have no really understanding value for you, okay? But if you want to really implement it, then you just need to take a look at the papers, because there they also explain how you can make them numerically stable, okay? So I'm just trying to give you the main idea how they work, so when you just open up your PyTorch and write down atom, you do know what every single value that you are choosing means, okay? And then, I mean, of course, if you want to implement, you need to just put a bit of more practice into it. So typically, the value beta 1 is the weight that you are just doing the moving average on the momentum with. That value of beta 1 is usually, both of them are close to 1, but beta 1 is smaller than beta 2 usually. So beta 1 is usually somewhere around 0.9, but the other one is very close to 1, 0.99, okay? And then you can always access the atom optimizer on Optim, and I guess this is the one which you usually use when you implement anything by PyTorch, right? But now you do know what is all of those parameters inside that meaning. Okay, everybody's clear? Any questions? No question? Great, so if you, okay, I have this. So let me just finish this one, and then we're going to have a break. So whatever we talked here is what we call it first order optimizer. First of all, if you just go ahead on torch.optim, so you write torch.optim dot, and then you press tab. Then you're going to see a very long list of optimizers. So I've not discussed all of them, but most of them are just going one way or another based on these approaches, okay? That's the first thing. And the second thing that you need, I think is a good thing to know, is that what we have discussed in this part of the course, all of them are what we call them first order optimizers. What do I mean by first order optimizer? It means that I'm only using the gradient, right? So they are gradient-based optimizer, which only need gradient. So you do just forward, backward, you compute the gradient. You have the gradient, you just do something with that, and then you find your next weight, okay? So this is what we call a first order. This is very good in terms of complexity because you just need gradients. So you just go once forward, backward on your neural network, and that's it. Yeah? For every single data point, of course. But there is another class of algorithm, which we call them second order optimizers. Those second order optimizers not only use gradients, but also they use Hessian matrix of your loss function. So meaning that you just, with forward, backward, past, you just compute the first or partial derivative of your loss with respect to every single weight. No, you need to compute the second order partial derivative of your loss with respect to every pair of weights in your model. And if your model dimension, I don't know, is 1,000, the second order computation needs 1,000 to power 2, like 1,000 squared. Now it's 1 million computations, correct? So you need, in that case, to know Hessian matrix. These kind of algorithms also are known as Newton-type algorithms because basically it comes with the Newton method, that how you can just minimize a quadratic function within one step. And this is a kind of boosted version of the gradient descent that we have. But the fact is that in practice we never use it. I mean, not never. If it's really necessary to use it, we can use it. But in practice we cannot really use it because it has too much computation. I mean, finding Hessian is like too much for us. We cannot really do it in practice with very large neural networks. Definitely if you use these algorithms, you're going to get much better convergence behavior, like you're going to converge way faster than simple first order algorithms. But the point is that you need to wait too much for computations. And then the question is which one is going to dominate. And usually is the computation is going to dominate in that sense. So we're going to drop second order algorithms. So as I said, this is a kind of huge computation. We usually, there are some approaches like quasi-Newton algorithms, which try to just look at the gradients and just estimate the Hessian matrix, because as you know, Hessian is or is the gradient of the gradient, right? And then you can look at the gradients and try to compute that or estimate that. But at the end of the day, still that is too much computation for us. So we really don't go for them in practice. So that's it. Let's just have a very quick break, and then in 4 minutes we're going to start with hyperparameter tuning. Okay? Okay, shall we go on? So, now, okay, so on hyperparameters and this idea of overfitting. So, what we did in chapter 1, we started, I told you that when we came to the question of how we can choose those hyperparameters in our neural network, I told you that you always assume up to some point that we have a genie which is going to tell us what is the right hyperparameter. And now the question is how we can just train that genie guy, right? So the first question that you might say is that, I'm pretty sure that none of you anymore think like that, but maybe a couple of years ago, people, when they started with machine learning, they would, or neural networks, they would say, okay, if we are able to increase the hyperparameter, like we have a deeper neural network, we have a larger or wider layers, shouldn't we always go for more hyperparameters, like larger hyperparameters? And then the answer is not really, because if we have a very deep and very wide neural network, then we're going to have too much computations, right? So do we really need that much of computations? Yeah?
I have a question about that. So if we have like too much parameter, like too wide or too deep, can't we face overfitting because like the neural network has just...
Sure. Yeah, this is what we are going to talk about right now. Yeah. Okay. So, but you're going to come with this question, as your friend asked, and that is that, okay, say we don't have any issue with computation, so let's go just for large hyperparameters. And then the answer is, again, not really, because you're going to see some kind of behavior, which we call it overfitting. Yeah? So meaning that you're going to get like a very good large capacity model, like it can perfectly fit into anything that you have. And then you do perfect training, but at the end of the day, you don't get what you want. Okay? So to just understand this, what is this overfitting idea, let me just start with a very simple example. Probably many of you have seen it in other courses about machine learning, but it doesn't harm to have it once again. And that is a classical example of doing a polynomial fitting. But now we want to do it with, neural network point of view. So say I have one machine which has this property. You give any input to this machine is going to give you this quadratic function at the output. Okay? So I give x to this machine, it's going to compute that guy, x squared plus 3x plus 3. Okay? This is going to be the output, and I don't know that polynomial function. I don't know exactly these coefficients 1, 3, 3 here. So what I want to just go for a machine learning approach, meaning that I give so many inputs to this guy, then I collect outputs, and then I try to fit my a kind of neural network into this model. Okay? Or sorry, into this data. Now, if I want to do machine learning, so basically the three main components that we need is data set, model, and loss. We talked about it a lot, so let's just do it that way. So first of all, let's just collect some data, meaning that we just get this machine. So I'm putting this machine here, and then I randomly select some x's, give it to the machine, and then look at the output, measure the output, and then put these two input-output into a data set. Right? Clear? Everybody's clear? So this is what I'm going to do, but say my measurement is noisy. This is something that happens, right, in practice. So I'm not going to get exactly this quadratic function, but I'm getting a noisy version of it. So there is a tiny bit of noise each time that I do the measurement, randomly added to this measurement. Correct? Now, I do this data collection, and then at the end of the day, I make some sort of data set which is of this form. So it's a batch of different tuples, pairs of numbers, and then x's are the input, and v's are the noisy outputs, right? Now, the second thing that I need to do is to go for a model, right? And then for a model, say we know that it's a kind of polynomial machine, meaning that the input, whatever it is, the output is a polynomial function of that, but we don't really know what is the order of this polynomial function. So maybe we're going to consider some general order P, and then we want to just design one architecture, one neural network, which implement this function for us. Okay? So what I'm going to do, I'm going to say, okay, if I want to compute a polynomial function of x, I can say this is a W0, W1 times x, and so on till WP times XP, right? This is polynomial order P of x, correct? Now, I can open up that guy, so I can look at it in this form. So I could say it's a vector of weights, right? Being multiplied by x to power 0, because that is 1 here, and then x to power 1, x to power 2, till x to power p, right? So if I call this vector to be vector h, then basically what I'm computing is this linear model W transpose times h. Yeah? So I can think of this polynomial as a kind of neural network. And how does this neural network look like? It's going to have just one hidden layer, and this hidden layer is going to compute those polynomial, those power functions, right? And then everything at the output of that polynomial, hidden layer, is going to be combined linearly. So basically, this is going to be one hidden layer. So I start from an input x, and then say the weights here are specified to be 1. So x is multiplied by 1, so it's going to be itself. Then I have neurons, and these neurons basically just compute the power, the corresponding power of my input. This is the activation, correct? And then if I get the output of these neurons, and then I add them up with some weights, W0 to WP, and just linearly combine them. So I put this line here to just indicate that the activation function is linear. There is no nonlinear activation here. Then the output is going to be exactly that polynomial, right? Everybody's clear? So it's not a big deal of neural network, but it's still a neural network, right? With one hidden layer, correct? Now, what is the hyperparameter here? Any idea?
Number of
P, exactly. P is your hyperparameter, right? You need to fix it in order to have your model explicitly written. So your hyperparameter here is P, and what you want to do is, how can I choose that P? Because you don't know what exactly that guy is. So if you want to do the training of this neural network, this is basically a regression problem. Why? Because your labels are real value. Those V value, the measurements that you do at the output of your machine, they are all real values, right? So if you do that, then, for regression, we talked about this. You did it in your first assignment. You basically just use a squared error as your loss function, meaning that you get the output of your neural network. You subtract it from your true label, and you square it. And then this is going to be the loss function, right, which is measuring the loss between your output and the true label. And now you have everything that you need for training, right? You have the model, you have your data set, you have the loss function. The only thing that you should do is to just do the training. So let's do the training together. So if I start training, I'm going to get my data set. Probably I just break it into a training data set. Not probably, definitely I'm going to break it into training data set and test data set. So I just keep 10% for testing, 90% for training, for example. And then I start doing gradient descent and that. You could guess that this is a very easy problem. So probably I don't need to break it into mini batches even. I can just do full batch training, right? So I just pass forward, compute the gradient. And once I computed the gradient, I update my weight. I keep on doing till the training is over, right? And then once the training is over, I get that trained model, and then I just do the testing, right? But before I start doing this, I should specify value of P, right? Now, if we get back to that very naive statement I said at the very beginning, I told you, like, if we go for higher hyperparameters, it's always better, right? So what does that mean? Or how does it reflect on this problem? This means that if I increase the value of P, it's always better, right? Because if P is order 10 and the true one is 2, I'm definitely sure that any polynomial of, if I'm thinking of a general polynomial of order 10, this includes that polynomial of order 2 as well. I just need to put the corresponding weights to be 0, correct? Yeah, this is a naive way of thinking about it, but if I plot the test risk after training for different values of P, you're going to see such a behavior. What is it? So here, as you can see, this is hyperparameter P, the order of the polynomial. Okay? What I'm doing here, I start with p equal by 1. I do the training, I test. Then I get one test risk, okay? And then I plot it here. This is the first one. Then I put, sorry, that is 0, of course, sorry, this one. And then I put p equal by 2, and then again I do the training. When it's over, I do the test. And then I get the risk. I get it here. I make it 3, 4, and so on till 10. And as you can see, at p equal by 2, which is the right choice of p, this is minimized. But anywhere but that is going to be more, right? So now, what is the thing that is happening here is that, I mean, obviously this is clear that before p equal by 2, this is not fitting because the model that we have is unable to mimic a second order polynomial, right? It is a constant first for order 0, and then it is linear function. None of them could mimic a second order polynomial, right? But what is happening at 3, 4, and so forth is that you have a polynomial which is able to mimic also a second order polynomial, but it is not mimicking the true function that you are looking for. This is actually where you say that we are overfitting, meaning that we are actually getting the data and then we are trying to just fit it into a very, not very, potentially very, but a larger capacity model, and then that fitting into that one is so perfectly matched to the data that we have that any new data that we give to it, it's going to fail in properly predicting its output. Okay? So this is the idea of overfitting, meaning that you get your training data set and then you train your model, your neural network, on that training data set. And this is going to fit perfect on that one, meaning that if you give any single data from your training data set into this trained model, it's going to give you exactly the thing that you want at the output. But it is unable to generalize. So the term generalize is quite important now. Okay? The idea of generalizing, it means that if I now give you a new data out of that data set, the training data set, it's not going to do the thing that you want. Yeah? Whereas there exist models which do not give you perfect output for your training data, but they are still doing better when it comes to the test data. So they are generalizing. So when you get out of your data set, training data set, they can give you still meaningful output. Okay? So this is the idea of generalization. This is not something coming from Mars. It basically says that, I mean, some model that generalizes, it simply does what you want, right? On any new data that you have. Okay? So if you just train it, put it in your pocket, then in future, anywhere with that kind of data, you're going to do fine. Okay? Clear? So this is the idea of overfitting. So now, the question that you might ask is that what is happening really in this overfitting? Okay? So this is the true function that we had in the example, the dummy example. So in the dummy example, we had a second order polynomial, right? That is the blue dashed line. But what we have measured is a noisy output, right? Meaning that you have a couple of samples. The first sample is here. I mean, if you could have really sampled the output, you would have been here, right? But you couldn't do it because you had a measurement noise, so you got here. Correct? Again, at this point, if you could have sampled exactly the correct output, you would have been here. But now you're sampling a noisy version. Clear? Now, if you are going to just look at those red points here and try to just fit a very high dimensional function to it, it's going to look like this, right? A very high dimensional polynomial. Well, high order polynomial, sorry. Yeah? So if it is, I don't know, I think this is polynomial order 5, it's going to try, I mean, what you fit is going to try to pass through all of those points. And since it is higher order, it is able to just do that, right? But the moment that you get out of the set of your data points, then you're going to see a huge difference, correct? Like, for example, here, you expect that this guy goes down, right? So if this is the second order function, and then you have these sample points. When your polynomial passes through them, your model, at this point you're going to see if you get a new test data set. So if I give you a new point, which is here, you expect to get somewhere close to this one. But this model that you perfectly pass through those training data points is now giving you a very different thing, right? So this is the reason we call it overfitting, because we are actually fitting it more than it's necessary on the data, which we do know that it contains some order of noise. Here? Got the idea? So now, if I instead just fit or focus on the second order polynomial, I mean, second order polynomial could not behave like that, right? It cannot change curvature. So I just can match it perfectly to the available data, which this guy is going to be a better approximator of the original true function. Correct? There is also this possibility that I go below the order that I need to be. Like I go for a linear function, right? And then definitely there I cannot fit anything, because that data that I do have, is coming from its second order function. And this linear function is unable to mimic that function, right? So this is when we call it, we have underfitting. So underfitting simply means that your model is unable to fit into your training data. And of course, it's unable to fit as well to your test data as well, okay? So this is usually not the case in practice, because this simply means that you're, like in this example, you're thinking of a very low order polynomial. And as you know, the models that nowadays we're working with are very huge, right? So they have enough parameters to mimic pretty much any function. The point is that they could be overfitted on the data that we have. So underfitting is nowadays not a problem anymore with the computation that we have right now, okay? Usually we have overfitting, but just to know that it also exists, okay? So this is a linear function. Whatever you do with this linear function, you can never mimic the behavior of a second order polynomial, right? And this is underfitted. Sorry, you got a question? You had a, no, sorry. So that's it for underfitting and overfitting. And then the question that you might ask is that how we can deal with overfitting. So the issue of hyperparameter tuning, or finding the right hyperparameter, is basically deals with combating the overfitting, okay? So there is no, say, put it that way, there's no concrete prescription that, okay, take this algorithm and go and compute your hyperparameters with. At the end of the day, you're going to take lots of intuition into account. But one of the points that you can check is that whether your model, after choosing a bunch of hyperparameters, is going to generalize or not, or it's overfitting. If it's overfitting, this means that you need to tune those hyperparameters. So the very first step that you can do is to just tune those hyperparameters. And how we can do it, we can simply do it by doing validation. Meaning that we had the whole data, right? And then we just split that one into one part for training, one part for testing, right? Now this part for testing, we again split it into two parts. One part for validation, one part for final testing to check the generalization. And then we have this validation, which is neither your test data nor your training data. Now you choose one hyperparameter, you train on your training data, okay? And then you go on your validation data set and you test it on that one. If you see that you are seeing the thing that you want, then your hyperparameter is doing fine. If not, you are going back, you change the hyperparameter, and then you again do the training. You again test it on this validation set, and then you see whether it's working fine, working better or not. And then after repeating, going back and forth a couple of times, then you get into some choice of hyperparameter, which is making some sort of sense. So this is the whole idea of validation. So you're going to just choose different choices of hyperparameters, and then among them, going to take the one which gives you the best performance or the minimum risk that you get inside validation. So basically what I did in this graph for you was a sort of validation. Because I started with p equal by 0, I increased this P one by one, and for each of them, I just trained it on my trained data set. And then I went on another data set, which is now the validation data set, and I just validated my trained model, right? And then I get this curve for different choices of P, and of course, this guy is giving me the best or minimum risk, so I'm going to say this is the right choice, this is how I do the hyperparameter tuning, okay? So, moral of the story, hyperparameter tuning, we can do it simply by validation, correct? But now, given the kind of neural networks you hear nowadays about, do you think doing this validation is a kind of possible thing, feasible thing? It's not feasible. I mean, think you have tens of layers, and each layer has even if you think of MLP, not like much more advanced architectures. Even in this one, you have so many layers, each layer has specific width, and then you need to just choose all of them, and then for each choice, you need to just do the validation and get back to the next choice. So this is pretty much impossible. It's a huge space that you need to search. And this sort of exhaustive search is not really a feasible thing. I mean, you might try it to just test whether having 10 layers or 12 layers, which one is better. Maybe you can try it if you have a few finite number of choices. But if you really have a huge space of hyperparameter, that validation is not really the thing that you can do. But what you do know out of this discussion is that if you don't do validation, the thing that could happen is that you can still see a sort of overfitting. So the overfitting could happen if you don't have the right tuning of hyperparameters. Now, one thing that I could say is that in this simple example of the polynomial, if I could just choose P very large, where I'm sure that it is much more than 2, and then I pretty much mimic, it can potentially mimic order 2. I am not in an issue with respect to hyperparameter because my hyperparameter is large enough that gives me a guarantee that the model can represent my data. But the issue is that when I do this, I'm going to have overfitting if I just do the training naively. And then the question is that, is there any way that I just choose that large hyperparameter, but I can avoid my model to get overfitted? Because if I can do it, then I get rid of that validation, right? Correct? So I put order of the polynomial to be 10, but I'm pretty sure that it's not going to overfit. Yeah? So there are approaches. So the moral of the story is that the main thing that we need to know is how we can avoid our model to get overfitted. And if we can do this, then tuning hyperparameters is not a huge deal for us anymore, because we basically just choose them intuitively, the one which is large enough and fine enough. Yeah? I do know that it's a kind of simple function, so I just choose a very crazy big model, right? Large number of layers, huge layers, very wide layers. But the only issue that I might have is that it's going to overfit, right? So if I can avoid that guy to overfit, I don't need anymore to just specify the number of layers, right? I mean, it's not a crucial thing anymore. You got the idea? So the question here then, the important question is that how we can just avoid having overfitting. And the main approaches that we do in practice are regularization, dropout, which is a kind of regularization, data augmentation, things like that. I mean, validation that I talked about in the previous slide is another approach. But as we do know, this one is not a very effective approach when we have a large space of hyperparameters. Now, if you want to just understand these different approaches, the first question that we need to answer is that when exactly overfitting is happening. And of course, you have one answer for this one, when your model is huge as compared to the data that you have, right? So the first answer is when your model is too complex as compared to the learning task that you have. Because in the dummy example we had, we wanted to learn a second-order function, a second-order polynomial, but we had a model which is order 10, right? So it's much larger than the original function that we are looking for, and because of that, it could overfit, right? So Now, if I want to just reflect it into the world of neural networks, I could say I have a simple function, simple classifier, but now I am using a very huge neural network to do that, right? And then if I do that, I potentially get overfitted. Yeah? So my model, which is the neural network, is too complex as compared to the learning task that I do have. One thing that people usually say is that the model has large capacity. And by large capacity, I simply mean that it is too complex as compared to what I'm going to do. This doesn't mean that capacity has no meaning. I mean, capacity has a very concrete meaning if you want to define it. So basically, capacity means the space or the dimension of the space that your neural network or your model can represent. But for our case, it basically means how many learnable parameters, how many weights we do have. Okay? So once again, when my model is too complex, when it has too many weights, what I do know is that it's very capable of getting trained for any function. And this is a great thing. I can just use it. But the issue is that if I use it on a data, I could potentially get overfitted when it's too complex as compared to the target learning task. But the whole issue is that I don't know how complex that target learning task is. I didn't know at the very first place that my polynomial is of order 2. Yeah? If I would have known this, I wouldn't have chosen 10, right? But when I don't know, I only can say, okay, whatever this machine does, it wouldn't be more than order 10. So let me just go for order 10. That's fine, but I might get overfitted. Yeah? Everybody's clear? So I hope that you get the core idea. Okay, now, we do know the first answer, or model is too complex, then this is going to make overfitting. But is there any other point of view on overfitting? Like, is there any reason that we can give for overfitting? And the other reason that we can give, or other point of view on overfitting, is about the data set size. Now, one thing that you should pay attention right now on is that overfitting is a kind of behavior you see on your trained model. And it doesn't mean that it's happening from independent sources. No, it's happening at the end of the day because what you have trained is not generalizing. That's it. Yeah? But you might try to find some root or reason for why this is happening so that you just get rid of that issue to reduce the overfitting. So one of the things is that when your model is too complex. The other thing is when your data set is too small. And again, they are the same thing. When your data is too small, it means that the model that you have chosen is too complex. But then you can do two different things. You can either reduce the order of your model, or you can increase the number of data that you have, right? So how can you see this impact of data set size on the overfitting? Let's get back to this polynomial approximation or fitting that I showed you. And now consider two different cases. So I told you when I wanted to just do polynomial fitting, I just started with a bunch of x's. I just gave those x's to my machine. I just measured the outputs, right? And then how many of them I do? I'm going to do two different experiments. Once I'm going to do it with 20 data points, and then I fit my model. Once I do it with 4 different data points, and I again fit my model. And in both cases, I'm going to set p to be 5, which is larger than the original order 2. Correct? Everybody's clear? Now, what's going to happen? So now I'm going to go and do the training, and I want to see how this trained model, or basically the fitted polynomial, in both the cases is going to get to be as compared to the true function. So this was our true function, as I told you. And then if I have just a few data points, then I'm going to perfectly fit that order 5 to that one, right? And then this could potentially pass through the right points. So here is exactly 4. But then it could potentially get very low, or maybe here as well. So it's going to get like this, Yeah? And then as compared to my true function, it could be much different when I get into another point, correct? But now, if I increase the number of points here, that function needs to fit into them as well. So it gradually tries to approximate everything, right? Correct? And then it's going to match the true function much better, right? So instead of reducing the order of my model, I can increase the number of samples that I have. Clear? So if you just increase the number of samples, then that function could potentially just move around that true function, that fitted function. And this reduces the amount of overfitting. So everybody got the idea? Yep.
I have a question from the previous idea. I was wondering, for example, in a real world problem, sometimes we do not know how complex is our
Yeah, of course. Yeah.
task.
Yes. Yeah, this is what I told you. I mean, the model that you have are pretty much capable of doing anything, right? You want to do, I don't know, 10 class classification in MNIST if you put like 2 layers of MLP. I mean, it can just pretty much do any classification for you. So you do know that your model is complex enough to solve your problem. But then the issue that you are afraid of is that now that I have very complex one, it's going to overfit. So how can I get rid of that one? Yeah, right? And then this is one way of looking at it. So maybe we can reduce the capacity of our model. But maybe instead of doing that, we just increase the data samples, right? Increase the data set size.
So sometimes it's not also
Available, yes, and then we go for regularization. Okay, this is going to be the next one. Okay, but right now, everybody's clear how this data set point of view, data set size point of view, gonna interpret to this overfitting idea. So more samples is gonna make your very high capacity model it's going to give it less chance of getting overfitted, right? But when you just fit it into very few data, then you have the chance of getting outside the true function. I mean, I do know that you have the feeling that I try my best to finish a part, but if you have a question, it would be better that you ask. So everybody's clear. I guess this is a quite simple discussion. But if it is not clear, just let me know. Okay, great. So that is the next thing. So you might tell me then again that, okay, this is again a good idea, or a good point of view that if we have a few data, then we have higher chances of overfitting, so we need to increase. But how large is it enough? And then again, this is, as I told you, exactly depending on your model capacity. The more complicated model you have, when you have too many learnable parameters, meaning that you have a very high capacity in your model, potentially you need more data samples, and it's not a very magical thing. I mean, of course, they are two different sides of the same coin, right? Correct? Okay. So the second answer that we could give into the overfitting, so instead of saying that our model has very large capacity, the other answer that we could say is that our training data set is very small. Like, if I increase the training data set size, then I'm going to get again rid of that overfitting issue, right? So this is the second answer. The third answer is actually much more interesting, and that is the answer about co-adaptation. So another way of looking at this overfitting is the fact, or thinking about it, that your model is not only, when it is too complex, when you have too many parameters in it, it's not only getting fit into the true function that you are looking for, but it is actually getting fit into that one plus the noise that we had. Okay? So let's just get back to this dummy example that we had. So in the dummy example, we had the polynomial. So let's just use one high capacity neural network, which is for p equal by 5. So I'm going to put my model hyperparameter larger than the true one, 5. and then I'm going to have 8 different noisy data samples, and then I try to just do the training by stochastic gradient descent or full batch gradient descent, doesn't really matter. Okay? Now, when I do this training, first of all, how many parameters do I have in this model? When I have polynomial order 5, how many weights do I have? Do I need to train? 6, exactly. So W0 to W5, correct? So you're going to have something like this, W0 to W5. And what you're going to do, you're going to start with one initial value. You compute gradient, you just update, right? You keep on doing till some number of epochs, and then you stop, correct? This is the way we do a stochastic gradient descent. So say we start with everything being 0, okay? Now, what do I want to get into? Is this guy. Because if you remember, our true model or true machine was of this form. It was v equals by x squared, I guess, yeah, plus 3x plus 3. It was this guy, yeah? So this is, 1 here is W2, 3 is W1, this 3 is W0, and anything else is 0, right? So W3 is 0, W4 is 0, W5 is 0 as well. Correct? Correct? Everybody's clear? So what I want to end up with, I want to end up with 3, 3, 1, 0, 0, 0. This is the vector that I would like to end up with. Correct? Yeah? Now, I'm going to be out of here after 5 minutes, so just please just respond. Yeah. Okay. Great. Okay. So now I want to end up with this guy, and now I'm going to start with some initial value. I told you I put everybody to be 0, and then I keep on training. So I do T1 iterations, then I end up with this guy. I go for T2 iterations, then I end up with this guy. So of course I'm not going to end up exactly with that one because I do know my data set is noisy. But the point here is that the thing that I end up here with, as you can look, is not that much different from this one, right? I started from 0. My first entry is just going gradually to get close to 3. That's fine. The second one I started by 0. Again, I gradually went up to get, again, close to 3. The third one is getting close to 1. Of course, the remaining ones are something non-zero, which is not perfect, but they're not that big, okay? So that one is not going to give me a very huge difference to the, hopefully, to the second order, the true function that I'm looking for, right? But let's say that I do not stop at iteration T2, and I keep on iterating, yeah? So you can potentially keep on iterating over and over and over. And if you do that, then at some point you're going to see that these other guys are getting much larger, and these ones are getting much different from the ones that you want. Now, what is happening here? So I started from everything being 0, then I gradually got close to what I wanted, this W star, but I was too greedy, I didn't stop, I kept on training, and then I got overfitted, right? So the thing that is happening is that initially I'm just going to just fit my model into the true function because that is the envelope that the whole polynomial, whole samples are on, right? But once I fit into that, since my model has higher capacity, when I start to just keep on doing the iteration, it just tries to fit its other weights to pass over those points perfectly, right? So the thing that is happening is that I am initially getting perfectly or close to the original envelope, which is the true function. But at that point that I am just getting the true function, now I am going to fit into the noise that is added to my data. Yeah? This is the idea that people call it co-adaptation, meaning that your model initially starts to get into that second order polynomial, which is the whole envelope that you have. But once you got this, so say this is my second order polynomial, so I have these samples around it. So I start with just training, and initially I have nothing, but at some point after some number of iterations, I get into something like this, which is a good estimate of the original second order polynomial. But at that point, when I'm just fit into the true function, when I keep on training and training and training, I just change those weights so that I make this guy pass through this one, and this guy pass through this one, and this guy pass through this one, and this one pass through this one, right? And then this can potentially just make at other places, the behavior of my approximator very bad. Clear? So this is a kind of co-adaptation. So you're just making this, noisy ones to fit perfectly, and because of that, the thing that is happening at other points you are just getting a sort of divergence from the true function. Okay? So this is a kind of behavior that we need to just stop. Yeah? We need to just make it not happening. Okay? So if you want to just see how does it look like in practice, so if you just keep on training that model as I told you, so if you start from 0 and you keep on training, and at every single iteration you just compute the difference between this weight and the target weight that you are looking for, your empirical risk is always going down. And this empirical risk is the training risk that you compute. And of course it makes sense because you are just perfectly fitting it into your data, right? But your distance from the optimal point, or the true model, is going to just get down, and at some point it's just start to increase, right? So this is the moment that actually going further training is not doing anything for you. Clear? This is the moment where you are starting to overfeed. And if you could have understood that this behavior, you could have stopped here, and then you would say, okay, given that large model that I do have, this is the best thing that I could see. You got the idea?
Yes, so I have one question.
Yeah.
So the number of iterations can also go for overfitting?
Yeah, of course, of course, of course. I mean, how do you detect in practice overfitting?
Yeah, I just talked about the parameters and some number of parameters or something like
It's not only that, yeah, of course, of course. But the point is, again, that I cannot just test this number of, I cannot set it from in advance, right? So what I'm going to do is, like later I'm going to do regularization, but I hope that you get this idea that when you are overfitting, you potentially get into the true thing that you want, the best approximator that you want, but if you just naively keep on training, then you're gonna just get away from that, right? And this is not something that you want. You just want to stay there, right? Okay, so I really hope that I could finish this, but I cannot, so maybe I just take a look at this one, right? So I'm going to start from this point on Thursday. So moral of the story, this behavior of co-adaptation is simply, as I told you, it simply means that when you have a very large model, when you start training, you are gradually going to capture the true model. But since you have a very high capacity, then at some point you start to just overfit, meaning that you just somehow train over noise simply. And because of that, your model at other points are getting to be far away from the true value. So ground truth. So this is the idea of co-adaptation, and the way that we get rid of it is regularization, meaning that we are going to just penalize that training empirical risk in a way that the moment we start to see that co-adaptation behavior, it naturally stops. Okay? So we're going to talk about it in some details next session on Thursday. And as I told you once again, so just once again, these three things that I told you, like large capacity, small data set, co-adaptation, all of them is like you have one thing which is overfitting. You're looking from different points of view, right? I mean, if you didn't have large model, this co-adaptation would have not have happened, right? So you don't think that they are independent things leading to overfitting. There's the same thing. At the end of the day, your model is too complex, right? But there are different ways that you can look at the overfitting. And this co-adaptation is the most practical one, which you always know, right? So you just plot the test risk, and you see that it goes down and then it goes up. Then you say it's overfitting. The reason is simply because of this co-adaptation. Okay? Everybody's clear? So we're going to continue with this one on Thursday. And one thing, I mean, in the that self-practice, I think the last written question is on some data processing thing. I don't think that I'm going to cover it next Thursday. Even if I'm going to do it, I don't think that it's fair to have it. So our exam would be up to this point. Okay? Clear? Up to this page, yeah. Up to this co-adaptation, right?
What's covering this Thursday will not be on the exam.
No, it would not be in the exam. Yeah. Okay. See you on Thursday.